use that for, I don't know, whatever it is that you choose to. I worked with many types of different applications, as well as many different types of bridging protocols, interoperability things, essentially a lot of things. And then I also have my own startup, built it using smart contracts, connecting it with things. Essentially, it's like a influencer marketing platform, programmatic influencer marketing platform. So worked with smart contracts as well. So have, I would say, pretty general overview of the different things. Oh. So we're going to be exploring the different types of bridging situations. The simplest one is that I want to transfer, or in this case, Alice wants to transfer 100 USDT to Bob from Ethereum to Avalanche. Ideally, Alice wants to work with a trustless system where it doesn't depend on external third-party validation. She also wants it to be extendable so that it can work with other different blockchains without too many changes. And number 3, which is important and should always be considered when creating any type of bridge, is that the liquidity that is created can be actually used. What is a bridge? Essentially, a bridge is transferring assets from one chain to a different chain. It can be from a layer 1 to a layer 2. It can be from layer 2 to layer 2, layer 1 to layer 1. Any type of asset transfer between different types of blockchains. They all have, let's say, different design decisions, different things that make them usable and fit for specific use cases. And we'll explore some. First, let's explore how an externally verified bridge works. So I send tokens to a bridge deposit contract on a source chain. This can be Ethereum, this can be Avalanche, this can be an L2. Essentially, we receive that request, and then we achieve a set of consensus. Like, we agree that this transfer did happen. As a result of this agreement, we then mint or unlock a bit of tokens on the destination chain. So if it's minted, there's a wrapped version. And if it's unlocked, that is typically the native version. And we'll see what the difference is between those things. But if you've ever used multi-chain, they have a token called any USDT, any USDC. So they have like their version of a wrapped token. Here are some externally verified bridges. So they basically have an external type of consensus where it's verified by a set of validators, and then as a result, the bridge operation occurs. These are typically trusted, right? I have to trust that they do the operation correctly, and then as a result, they do whatever type of results. But essentially, trust is one of the main regards, is that I have to trust that everything is verified correctly. Now, externally verified bridges have a high security assumption. Because I have to trust that they are, essentially that the transaction has executed, I have to rely on an external set of validators. So essentially, I have to trust the protocol that they do the actual bridge operation correctly, or I have to trust the multisig that's controlled by the protocol. So whether that be through different types of signature schemes like BLS wallets, whether that be through, let's say, like the validator scheme of like I have another blockchain that verifies other blockchains. Either way, I have a lower security, higher security assumption to enable this bridging. In addition, externally verified bridges typically need to have a high amount of liquidity deposited within their contract. So they need to attract a lot of VCs, a lot of people to put money into the application. Can we use a layer 2? Let's talk about natively verified bridges. So what is a layer 2? A solution built on top of a layer 1's consensus for the purpose of scaling privacy or similar use cases. So this is what we mean by natively verified. We are depending on the security of the native base chain. So that can be a layer 1, or if I'm creating a layer 3 solution, that can be from a layer 1 to a layer 2, so I'm inheriting the security of the layer 2, so on and so forth. So there can be multi-layered applications. But essentially, by natively verified, I mean that the L1 itself, or whatever contract itself, we're depending on their consensus mechanism for validating different types of operations that occur. So for example, here are some of the natively verified bridges. So we have like Arbitrum, OP, Manta, Base, Metis, Mantle, etc. So these are verified essentially by the L1. So a lot of these are layer 2 scaling solutions, and they're built on top of Ethereum. So we're depending on Ethereum's consensus in order to bridge to these ecosystems. How does it work? Well, first, we send tokens to a bridge, deposit, or withdrawal contract. This can be on layer 1 or layer 2, depending on the operation. But typically, if it's from layer 2, then you want to withdraw. If it's from layer 1, you want to deposit into the layer 2. The natively verified bridge receives the request, sends it to the destination chain using the native security. So this can be from optimistic solutions. This can be from ZK solutions, depending on how it's implemented. But typically, I need to have layer 1 to verify and guarantee security for the chain. So essentially, I rely on layer 1's consensus mechanism to make this withdrawal. That's the important part. The destination chain mints or unlocks a corresponding amount of tokens. If you are bridging to L2, they're typically minted or burned. So if I'm bridging, let's say, from like one ETH from Ethereum to Metis, I am locking that ETH on L1, and then the L2 side mints the corresponding amount of ETH on that side. And so I have that 1 ETH on that side. And then for L1, that's when I said that the tokens are locked and then minted on L2. If I want to withdraw, then they're burned and unlocked on L1, following the different types of schemes, optimistic or ZK. Can we make this type of scheme better? We have a natively verified bridge that can only communicate with the base L1. So it doesn't work if I want to communicate from Ethereum to Avalanche. So on that side, I can't really, I can't inherit the security of Ethereum while bridging to Avalanche because there's nothing that really connects the two. Because Avalanche isn't built on top of Ethereum. It's its own independent L1. But I can transfer assets and have native security if I interact with an L2 on the same, let's say, base chain. So for example, if I'm bridging from Metis to Optimism, I can inherit the security of Ethereum because that's the common ground. So essentially, how this structure would work is that if Avalanche is separate, Ethereum is also separate, but Optimism and Metis are both inheriting Ethereum security, I can basically transfer assets from either one while still retaining the security of Ethereum. But I can't do that when communicating with Avalanche. So this is what we mean by multi-chain. That example of connecting Avalanche to Ethereum, that's cross-chain. That example when connecting Optimism to Metis, that is multi-chain. So I'm inheriting the security of the L1 to process the bridge transaction. Now, question is, this is like the billion-dollar question, jillion-dollar even. Can we get native security and cross-chain communication? And this is where we have locally verified bridges. Typically, the IBC, inter-blockchain communication, is like a protocol. It's a messaging layer. We all hear that it's compared to TCP/IP. So how we do messaging in, let's say, the Web 2 world, or even the Web 3 world, we communicate via HTTP. And then I need to send data from one place to the other. In order to do that, I have everyone agrees on a set standard to base that communication off of. IBC is that standard for cross-chain communication. Now this relies on light clients basically sitting in between the two different chains. So I have one line clients on Avalanche and the other light client on Ethereum. I use the native L1 consensus to achieve the bridge. So I have that common messaging layer. And then I'm able to basically say that when I deposit something on Ethereum, I want to withdraw something on Avalanche. And as a result, the light client would verify the transactions that take place on each layer 1 and be able to send a corresponding amount of tokens or like unlock a corresponding amount of tokens on the other chain. And then Cosmos implements IBC. So that the Cosmos is like a sort of like layer 0 network where like it connects the different blockchains together, kind of like PolkaDot as well. So can we make it better? So locally verified bridges can connect with, let's say, any different chains that exist. We don't really need any additional trust assumptions since we're basing this verification off of the layer 1. So because I'm basing my security off of the L1, I don't have to depend on any other external network or external set of validators in order to make sure that this transaction occurs. I don't have to trust anyone, essentially. Though, one big issue, liquidity is not guaranteed to be present or can be used. Now, what do I mean by that? So as an example, IBC Fun is let's say the interface towards all of this like cross-chain communication. And in my example, remember how I said Alice wants to send 100 USDT to Bob on Avalanche. So as you can see, I'm trying to send 100 USDT from Ethereum to Avalanche, but it says down here that the route was not found. So this means that liquidity wasn't provided for that to be unlocked on Avalanche. So no route can be found, so therefore no assets can be transferred. So it's super secure, but nobody can use it. That's basically unless someone provides that route, provides that liquidity, implements that protocol, et cetera, et cetera. So a lot of things need to be done before that can happen. Let's sum it up. We've reviewed the different types of bridges: externally verified, natively verified, and locally verified. We want, ideally, a bridge that is trustless. So again, third-party validation, so externally verified, out of the question, at least in what we're looking for. We don't want to depend and trust someone else to facilitate the bridge transaction. Extensible. It can work with it to any other blockchain without needing a ton amount of change or implementation. And finally, liquidity optimized. We can actually use the network because people have, we're not depending on a lot of people putting a lot of money before it's actually being adopted. Now, let's talk about zero knowledge and where, let's say, the idea of burning bridges comes from. Current zero knowledge proofs can be built for multiple use cases, but there's two main use cases that have been adopted by a lot of solutions, from like identity solutions to scalability solutions to privacy solutions, right? But two main use cases for ZK proofs are, first, privacy. I don't have to reveal the information of whatever that I'm trying to do. And the other is verifiable computation, that I can verify that I did execute this transaction or this batch of transactions and therefore can unlock some amount of funds. That's how ZK rollups work. So how does the scalability rollup work? We take a batch of transactions, generate a proof, and then send the proof of the computation to L1 to have it natively verified. And that way we can basically be sure, use complicated math to facilitate bridging between a layer 1 to a layer 2 ZK rollup and back. Now, can we make a ZK proof bridge? It has been done, right? There has been different solutions that exist. For example, ZK Bridge utilizes layer 0 for liquidity and message passing. So they essentially went in and focused on, I want people to be able to use our network, and I want people to be able to reliably bridge between it. And I want people to also have a great user experience because there's actually money in the system where I can bridge to different networks. So in their solution, they focused on extensibility because layer 0 is implemented across different types of solutions, as well as liquidity optimization. Unfortunately, for the security part, we can take a look at the layer 0's like omni-chain model, and we have a lot of red things, scary. But essentially, I am putting my trust in layer 0, how layer 0 implements things, in order to facilitate the transfer. So they make it really easy to get the liquidity. They make it really easy to do all these message passing, but you have to trust layer 0. Now, another solution, ZK-Link. Say they use native ZK-proof verification, but they need to depend on external liquidity providers. So what do we mean by this? It's like, so the way that they do it is that they have multiple different proofs synced across the different networks. But in order to, let's say, facilitate a transfer from one network to the other, I need to deposit money into that bridge or deposit liquidity into that bridge. So it runs into the same problem as IBC does, where I need a lot of people to adopt liquidity across a lot of different types of bridges in order for me to actually reliably withdraw to that specific network. So it's trustless, right? We depend on the ZK proofs, how the ZK proof is generated, and we just use the ZK proofs. And it's extensible, right? It works with the different types of blockchains that they've connected. Unfortunately, it does depend on different types of external factors like VCs putting money in. So you need to have people to deposit a set amount of USDT on one network in order to be able to withdraw on that network. So can we make this process better? How can we use the liquidity of one chain and use it in another? And in this case, the problem that we're solving is primarily the liquidity. We need a network of usable pooled resources and a trustless, extensible system that combines them together. So this leads to a solution, potential solution to the problem, where we can take a ZK bridge plus an L2 and combine it together with ZK proofs as that messaging layer. So any deposit to the layer 2 would then increase the total amount of liquidity of the entire network of L2s. So the example here is 100 USDT deposited on Ethereum and 100 USDT deposited on Avalanche would net $200 of total liquidity across all the L2s. Now, let me explain this in a little bit of like this overview. We have a layer 1 Ethereum, right? We deposit 100 USDT on that layer 1 Ethereum. Now we have a layer 2 ZK rollup, right? And ZKM implemented, and I'll explain that, like how all of this, would connect to each other. But essentially, we have it so that the layer 2 acts as an interoperability protocol, same way that layer 0 solutions like Cosmos as well as PolkaDot would work, except this is deployed on a layer 2. So in this way, we have it so that the layer 2 can communicate with other layer 2s that implement that same protocol. In this way, we can actually burn 100 USDT on one of these layer 2s and then essentially generate a proof that I burned this amount of USDT on that layer 2 and then be able to redeem it on a separate layer 2 within the same network. So what this means is that I'm depending on native Ethereum or L1 security, and then I'm able to essentially generate a proof that I have essentially no longer have access to that 100 USDT. As a result, I'm able to mint it on the other layer 2, in this case, the one that's built on top of Avalanche, And then finally, the end result is that I would be able to withdraw it on Avalanche itself. Now, the one big question is, oh, well, what if there's nobody that deposited on Avalanche? Well, in that case, you wouldn't be able to withdraw on Avalanche. But you would still be able to mint it on the layer 2 that's built on top of Avalanche. So in this case, you can deposit to the Ethereum blockchain and then navigate it and put it into the ZKM blockchain. Or into the Avalanche layer 2. So in this way, you can transport liquidity very easily. You might not be able to withdraw to the layer 1, but you're still able to, let's say, if you're a VC, you're always looking at different narratives. You're looking at like, oh, what does this chain do? What does this chain do? What is like these different types of narratives? And so you're able to essentially transport liquidity very securely and still be able to use all of the liquidity that you've deposited. That liquidity isn't locked and you're just waiting for someone to bridge to Ethereum to get the fees from it. Now you're actually utilizing that liquidity within the layer 2 ecosystems and then navigating it across the different blockchains. So pros of this method. One is that it's trustless. It doesn't depend on third-party validation. There's nowhere that I need to depend on another blockchain in order to facilitate this transfer. I depend on the ZK proofs that then inherit the security of layer 1. So I'm able to basically guarantee that that amount was burned based on the layer 1's verification method. Interoperable. So I can, within this system, assuming that we have ZK proof validation or verification on other systems. So let's say on Solana or Move, right? If I have the ability to verify ZK proofs on those blockchains, I can technically connect this within the current infrastructure. So I can essentially expand this to other chains that are not at all related in terms of that same VM. Next is that it's liquidity optimized, right? I don't have to depend on a bunch of VCs with a large liquidity pool to provide liquidity for every single chain that we're going to integrate. Instead, I'm using the liquidity from the people that have already deposited to the L2 or to the L1. In this case, you know, there's whatever amount of millions of dollars that are even billions of dollars bridged to layer 2s that are just sitting there. In this case, we're depending on the people to fund all of these other, you know, layer 2 structures. So we're not depending on big liquidity providers to then, you know, hopefully someone bridges my protocol. No, I'm depending on just regular people to come in. And any bridged funds that enter the network can be used across all networks. So remember how, you know, that example for Avalanche. Well, that can be used for the L2 that's on Phantom. It can be on the L2 that's used in on Harmony or any other layer 2 that is essentially connected to a layer 1. We also have the benefits of L2. So right now, the benefit of L2 is either privacy or scalability. We can inherit that type of, let's say, positive relationships. So people are putting, you know, billions of dollars into L2s because they provide that scalability benefit or that privacy benefit. We can have native bridging benefits as well in combination with the scalability. So this is essentially the you know, we don't have to sacrifice the scalability and the interoperability. We can have it all in this case. You can have your cake and eat it too, essentially. Now there are cons, right? Remember the three things that I mentioned: trustless, extensible, and liquidity optimized. Unfortunately, this model, in order to be, let's say, adopted, it needs to be implemented by the L2 that essentially would allow the minting of assets on their L2 through this ZK proof protocol. So for example, in order for me to use this in, let's say, Optimism, I'd have to convince the DAO to essentially open up their L2 mint to be able to facilitate native Ethereum So that's how it's done right now. And the ZK proof bridging. So in this case, they need to make sure that everything, it's all audited, secured, and everything. But in this case, we can do this by creating, separate L2s that facilitate within this entire network. And then the idea is that since all of the liquidity can be used within this entire L2 network, you can easily transport it using the native L1 security. So it might take a matter, depending on how it's all implemented, depending on how it's all audited, depending on different factors, it can be a big consideration, especially if there's a large amount of liquidity sitting in this network. And all you have to do is just implement it within yours. So it does have to be implemented. So again, it does have to be implemented within the native bridge on the L2. And it has to be adopted, and you have to make sure that the ZK proofs are working correctly on every single implementation. One mistake potentially can lead to mass withdrawals of oh no. In addition, that example that I mentioned, in terms of the avalanche, where let's say nobody deposits on Avalanche, so everyone deposits on Ethereum. And let's say I bridge to the Avalanche-based L2 that's connected. In this case, I can't withdraw to Avalanche because there's no liquidity on there. But I can withdraw to, let's say, another chain. I can bridge to another chain on the L2 network that has liquidity on L1 to withdraw it there. So in this case, I'm able to, I can still access my funds, but on a different chain that's implemented. So maybe not Avalanche, but maybe back to Ethereum. In this case, what we're basically, it's like a bridge without a bridge. I know it's like the main problem that we're solving is that we want to bridge these assets across the different types of L1s. And so in this case, and I'm saying oh, well, you can't do that if there's no liquidity. But in this case, as a person that wants to operate within this entire network, if I'm just integrating a chain, I have liquidity within the entire L2 space that implements this type of solution. So I'm able to basically utilize different networks' liquidity and then be able to move it around seamlessly within these different L2s. And then if I want to eventually withdraw, I can do that as well, but it can be on a different network. So this is like a collective layer 2 that works across different types of ecosystems. And we can use it for bridging, we can use it for scalability, we can use it for these different types of applications that really bring benefits. Right now, we only have L2s that work on either privacy or on scalability. And so in this case, it works with bridging as well. Yeah, that's everything. And we have different types of resources. We're giving different talks as well based on these types of mechanics and designs at our hacker house. If you're interested in exploring the space of bridging and how this entire mechanism works, how ZK proofs work, how this can all be used together, definitely come by, speak to me, and I can get you in. But yeah, I guess any questions from people, how this all works, what the benefits of this. It sounds like there's too many downsides. Oh yeah. Oh, sorry. Just shout. Got it. Okay. So the question was, how did the different L2s talk to each other? The primary communication for this is that they talk to each other through the layer 2 acts as both a scalability layer as well as that interoperability. So they communicate with each other through these proofs that are generated. So in this case, we burn the USDT and then we generate let's say a receipt. This receipt can then be used to, let's say, mint an amount of assets on that native L2. So in this way, the communication is done via this burn address model via ZK proofs entirely. So we don't need to depend on external verification like it's done with other bridging solutions. So I don't need to depend on an external multisig or validators to be able to facilitate this. Yeah. So yeah, that's an important concept. Since we're inheriting the security of L1, essentially, if there is a reorg on L1, that it's like there needs to be some amount of finality present on that L1. So I can basically within this L2, I can basically I can use this proof that was generated. But I am, yes, depending on the security of L1, depending on that aspect of finality that is achieved on the layer 1 side. But essentially, I can use that proof that I did this action on L2, and then eventually, like it did get processed, it did get resolved. There might be that delay, right, where we want to reach that L1 finality, and there might be like built-in a system that waits for a specific amount of time. But in this case, I do depend on the L1 security. I do depend on the L1 finality to be achieved to facilitate this let's say bridge request. Sorry? Yeah, there might be a bit of a delay. In this case, like when I generate the proof, I could basically say that I have essentially verified this on the L2 side, and as a result, it will eventually be finalized on L1. So like eventual finality will occur on the L1 side because I post this transaction on L2, and then unless there's like some amount of massive censorship going from there, but essentially the idea is that eventually there will be some form of finality on the L2, and that's what we're doing with the different like L1 to L2 bridging and L2 to L1, is that we're essentially posting a proof saying that this did in fact happen, and then we're essentially trusting that the sequencer would eventually post that proof to L1 and to be able to withdraw from the network. So in this case, again, we're still depending on layer 1 security, layer 1 finality to achieve that, like the bridging essentially. Hopefully that makes sense. If anything, we can talk about it when presentation's over. Yeah. Anyone else? Okay. Awesome. Well, thank you, everyone. Really enjoyed giving this presentation. I'm going to give something similar like this, and then maybe go into more of the privacy use case and the implementation from something that based on not wormhole itself, like the bridge wormhole, but wormhole style bridging. And we'll talk a little bit more at the Hacker House. So if you want to find more about that, let me know.